I've been privileged to be able to work with and interact with Hans on a number of occasions over the last few years. He's someone I think who's got really deep insights into lots and lots of different areas to do with data curation. Deeply involved with a workshop that's going to be running at the end of the conference about how we look not at the costs but at the prices that long-term data archives store. But this morning he's going to be talking to us about stewardship of data in the marine sciences, in which you currently specialise. I'll hand over to Hans.
Thank you, Kevin. Good morning, everybody. I'm actually privileged again to speak here, and after this stunning speech, first speech, I don't know how to, well, if I can be compared to that. But first let me introduce myself in another way. Actually, I'm with the Alfred Wegener Institute, and my day job there is to do the IT infrastructure. And as a hobby, I became the speaker of the Helmholtz Association of German Research Centers on the matter of open access. Helmholtz is operating the bigger research infrastructures in Germany, such things as accelerators, Cancer Research Center, and indeed a ship or ships for marine research. And we have a working group on open access there, which particularly is interested or specializing in access to data. Let's say access to data. I'm becoming ever more open on the question of openness in data. Originally, I was educated as a physicist, and well, now being a physicist, originally I will begin with a physics example, an old one, because modern science is based on data since at least Renaissance. And so maybe some of you have heard about Kepler's laws, which you can see at the bottom of this slide. You may recognize this ellipse on which planets are moving, and this thing with the areas, which he discovered or published actually in 1606. And 12 years later, the third law, which involves some, well, is there a laser here? I don't know. Which involves a rather small table, which shows some data like the time of revolution of planets and the diameter of the ellipses, or the major axis of the ellipses, and their relationships. And there he found his third law. After 12 years, indeed. Oh yes, thank you. Just a button there. Yeah. So, and he got this from actually someone else's data, Tycho Brahe's data, which were the first quality data which enabled this table to be constructed. And you can actually see those data today in the Royal or the National Library of Denmark. I think it's also Royal Library. It's still there. You can photograph it. And a few years later, I think 30 or so, there came Newton, who is best known for explaining Kepler's laws. And the laws of Newton look somehow like this one, remembering from the first semester of physics, and everybody forgot about Tycho Brahe's data or contribution. This is what I wanted to say now as a historical example, which we are all still talking about in principle. Now, the information infrastructure of science at that time, 350 years ago, was, well, in its infancy. So this was a scrapbook from Galileo, and being a tutor in the first semester of physics, I would have said, well, Galileo, you will never become a good scientist when you keep on working like that. But he succeeded in explaining some things, didn't he? Likewise, the first scientific journal looked quite funny. So I tell you this because we are now in a situation using computing and using large-scale data infrastructures, which is quite similar to this kind of imperfect infrastructure. There are even articles which say, well, does computation threaten the scientific method? Because the problem is, there is a problem of reproducibility with computation, which you wouldn't think. But This was even in a newsletter from grid people, so I believe them. Also, now switching to the domain of marine sciences, I cannot but mention every second presentation that there is an experiment which is bigger than CERN, or CERN's LHC, which now I call the Argo fleet of buoys. There are now, this is an update from yesterday, 3,624 floating buoys around the world in the oceans, which measure the temperature and salinity in the first 2,000 meters of water. The point I would like to make is you will always see pretty pictures from the satellite people showing you the surface of the oceans. But there is much, much more below the surface. And the major point is, of course, that most of the open area of the oceans is about 4,000 meters deep. And so there's much to be discovered there. Even if it's only temperature and salinity and the currents which drive actually much of our climate. You can see here, this is Google Earth, somehow distorted, but you can see these green points you can get from the Argo Consortium KMZ, which shows the current positions of these buoys. And as you can see, there are not much buoys, in fact none, in this whole area, which is of course due to the pack ice. So there are areas due to pack ice, due to shallow waters and so on, where these buoys cannot go. And then there is something like, oops, oh yes, this was, first of all, I need to mention the infrastructure which they built to use those data actually. If you go into these points here, you will be led to pages showing some preliminary evaluations of each individual buoy's data, and you will find pointers to those two data centers which are actually handling these until now 1 million measurements, which are with the French Institute Pfeiffenberger, which is a partner institute of AVI, by the way, and the US Navy, interestingly. So it's a worldwide infrastructure to handle those data and to get some interpretations and daily updated maps of something which is actually a useful tool for many people, including weather forecast and other things. You can see it on their website. But if you look again at this area here, where nothing happens, I would like to point out this area, which is the Fram Strait between Spitzbergen and Greenland. This here is Spitzbergen. This is actually where the seed database is and the ice bears, watching them. And in between is an area where there is also 4,000 meters deep water. And the main point is that what you know as the Gulf Current, which brings warm water over here to the Arctic, it cools and goes back through Fram Strait. So even if there were Argo floats, you can't use them here, and they can't dive deep enough here. So there is much to be explored even beyond this biggest experiment in the world, using ships, etc., going elsewhere. This is a track line of Polarstern, our ship, going up here and doing things here. I think this was marine seismics, but you can do lots of things here. You can do biology, you can do geology, going there, picking up sediments from the bottom to see the climate history. You can have, you can look at, you can lower things and can look at beasts being there where nobody thought beasts were to be found, even a few decades ago. And so there's ample reason to go out there with ships still, such as it was done, let's say, in 2004 with Polarstern, with a project called IFEX. I want to mention this because this has also high societal relevance. You may have heard about this thing that Sahara dust is fertilizing algae blooms in the Atlantic. And so somebody came to the idea, well, let's go out and dump some million tons of iron fertilizer in the Southern Ocean, so to capture and sequester CO2, to let it sink to the ground with dead algae. So people had to go out there and find out if that would actually happen. They did, and they dropped some tons of iron fertilizer south of Cape Town into the Atlantic Ocean. And the point here is that on board there were around 50 scientists and students from 14 institutes, from 7 EU countries and South Africa. And they were oceanographers, biologists, chemists, and a lot of others doing what is now called biogeochemistry. And they even used, of course, some satellite imagery, as you can see here. So they dropped these tons of things, they measured the temperature of things going on, the speed of currents going around, and then they took samples, which you can perhaps see here, what kinds of algae are actually growing here, with and without fertilization, and then they drew their conclusions. And they did this for some weeks. So this is the kind of thing marine researchers are doing if they're actually working together. And the problem is, of course, how do you keep all this knowledge together when it's distributed around different disciplines, around different institutes, etc. So we thought, well, what we actually need to do is we need to not just preserve some of these Excel files and whatever the biologists have taken when counting algae and so on, but we need to preserve these things together, these data sets together with publications, and we need to connect these expeditions or projects with data sets and publications. And of course, it's always very important to have names on it, because that's important for the it's important to have the names on data sets, because some will not believe in data generated by certain people, and so on and so on. But it is well known. So what we did is, many years ago already, we had this table, we had this database connecting these expedition names, project names to the publications referring to these expeditions and projects in our institutional repository for publications, and our institutional or disciplinary repository for data sets named Pangaea, which you may have heard about already. So more recently we have done this whole thing as a graphical example. You can see here where this expedition happened, where they went from Cape Town, going around here and doing their things in some eddies. The main thing here is, if you have all of the data, how do you actually find out where interesting things have happened, where other people perhaps have measured similar things, and so on, because the whole thing is so distributed over the world. Here you can see there is again Pangaea. This idea of connecting publications to data has been taken up by others like Elsevier. There is now a cooperation between Pangaea and Elsevier, where supplementary data are being supplied from Pangaea to Elsevier articles in Elsevier journals. And so this program, which we set up here, has now been done by us during this expedition database or portal for our institute, which points to publications and data sets, which point to each other's again. This has been done now for some years. More recently, we have this thing with the persons. I'm just talking about pointing if we actually have PIDs, by the way, for each data set, for each publication, and indeed for persons. And now projects. I would like to point out here that One of the things, one of the most interesting things coming out of open air for me is that they forced, or the clause 39 actually forced people to include a unique identifier for a project in a metadata set. So this is quite important to me at least. But what about scalability? Let me show you this. This is an image which you can't read at all from 2007, 2008, the International Polar Year, which was a collection of projects. Maybe you can distinguish these hexagons here. I think these are about 150 hexagons, each of which is a cluster of projects, like IFEX. Each of this is a cluster. And this was supposed to be happening in the International Polar Year and to be done by 50,000 participants from 60 nations. And they spent about 1 billion euros to take a data snapshot of the polar caps for reuse over many more decades. The first polar year, by the way, happened in 1880 something. So we actually need to preserve all those data and keep them together potentially from these very, very diverse groups of people working on the data and having them stored probably only locally. So just to show you one of these hexagons, what the scale of the hexagon was, and the topics were, in this case, reindeer herding and climate change. And it, of course, involved scientific domains like climatology, oceanography, veterinary medicine, ecology, sociology, geography, and perhaps more. And, of course, it was also around the globe, around the Arctic. It involved different cultures, languages, and so on. So, an unprecedented thing this was in the ambition to collect data. And well, as we found out, actually there is a problem accessing IPY data still. The program manager of the IPY is actually my co-chief editor, has said there's very little data actually now available. So we go for it in a smaller way. We go it publication by publication. This was published in December. The challenge to keep global warming below 2 degrees centigrade. And this was referencing a data article in ESSD, and the ESSD article references the Nature article. Both were published on the same day, at the same hour actually, and we had to struggle. I think Bruce is here from Nature. We had indeed to struggle to make this work. This is a small technical problem which also needs to be solved. Quite a different approach to data, to more proper data management, is a recent thing we are doing now, a German data portal for German marine research. We can't do it for the whole world, not yet. So it addresses a number of things which are of high importance. And as you can see, we are addressing German research infrastructures like airplanes stationed in the Arctic, ships, and remotely operated things. We notice that there are highly different types of data operations here, like the difference between taking a snapshot somewhere, what's going on here now, get it, or long-term monitoring, that is taking every hour, every minute, or whatever, a data point and adding it to the database, which are quite different things when you're talking about publishing it or preserving it, making it persistently addressable, for example. These things are stored in a low number of data centers actually, but even then it's difficult to speak to each other if you have so very different constituencies, like a government agency and a research institute. But there is the requirement coming from the scientific community to create this coherent data portal, to get access to all of the data, which forced us actually to speak with each other now, this time about the data flow from research vessels via the institutions to the public or to the researchers or to whoever needs the data. So what turned out to be the easiest part, by the way, or the most productive part at least, was talking about the raw data. How we get the raw data from the ship into the data acquisition systems and then on to institutes. And this was just because we had developed this data acquisition system D-Ship. This was 10 years ago. Meanwhile, every of the German research ships has this system on board. But this, and only this, enabled us to speak easily about things. How we had to improve the station book, which is something like the lab notebook. All the other areas are much more difficult to approach because we have, even from institutions which are 100 kilometers from each other, so different approaches to data management in place. So we need much time to even develop a common language on things. Quite different things we experienced with the building of the portal right now is that we can now actually reap the harvest of having stored all the data for 10 years now with the referencing of each other. We can see these hub and spoke things from data, relating data sets to publications. So coming to my conclusions, I think that Earth science is a big data problem in that we are trying to find and exploit patterns in data and metadata, but it's much more heterogeneous and distributed than, say, the database of Amazon or Google or whatever, where this big data thing comes from. We need actually the linking between publications and data, not just for quality assurance as in ESSD, but also because the publications are the best metadata we can have. And I think I would like to coin this, that the publications are linking hubs in a digital assets ecosystem. And now this portal project forced us to, in a relatively small community, local community, to first find a common language. And yes, the point is that we now beginning to approach this thing of workflows from ship to dissemination as a whole, not just from the compressed data to publications, as in the case of the global carbon budget. Thank you.